All right, so today I think I'll just be helping you guys solve some of the uh, later problems from like Amy from recent years. And so our first problem today will be this one here, the number 12 from the Amy one from this year. And I'm sure many of you guys took this test, and I actually did not get this question right in the actual contest, but I'll do it again now. So let's see, we have a 12 gone, A1, A2, A3, A4, A5, A6, all the way to A12 as labeled around in the circle. And then 3 frogs initially sit at here at 0.4, here at 0.8, and 0.12. And every minute simultaneously, each of the 3 frogs jumps to one of the 2 vertices adjacent to its current position and independent of other people's choices. So for example, in the first minute, the frog at A4 has a 50% chance to move to 0.3 here and a 50% chance to move to 0.5 here. And then as soon as 2 frogs arrive at the same vertex at the same time, then everyone stops, and we want the expected number of minutes until the frog stop jumping. So in this problem, we'll just consider how many spaces from each, or how many vertices apart from each other each pair of frogs is. So since there's 12 vertices, and after every minute we know that each frog must be either on an even vertex or on an odd vertex. So there are only 4 possible configurations we can have such that no 2 frogs are on the same vertex. So one configuration is that all 3 frogs are 4 spaces apart from each of the other 2, which we call 4, 4, 4. An example of this would be the starting position 4, 8, 12. There's 3 other positions we could have 2, 4, 6. In an example of this would be a frog at position 2, a frog at position 4, and a frog at position 8. 8 minus 4 equals 4, 4 minus 2 equals 2, and 8 and 2 are opposite each other, and 8 minus 2 equals 6. And then there's another configuration, 2, 2, 8, and also I'm sorry, there's also actually only 3 possible configurations of frogs. So an example of this would be a frog at 0.2, a frog at 0.4, and a frog at 0.6. 2 and 4 differ by 2, 4 and 6 differ by 4, and to go from 6 to 2 without passing through this other frog, we have the sort of sandwich between the 2 frogs. You have to go the long way around. So it's 8 spaces, 1, 2, 3, 4, 5, 6, 7, 8, from 6 all the way around to 2. So in this problem, they want to ask us for the expected value of the amount of time it takes for a 4-4-4 configuration to have 2 frogs that are in the same position. So in order to do that, we would need to get 3 equations, we need to get an equation describing it. So suppose we had frogs at 0.2, 6, 4, 8, and 12, and because this case is symmetric, so let's so then we can consider what happens to. Then we can say what happens to the configuration when we move the other 2 frogs. Okay, so let's say that the frog at point 12 moves to point 1 then. So then the distance between the frog at point 1, the frog at point 3 is now only 2. And then notice what the frog at point 8 then does. So no matter whether frog 8 moves to point 7 or point 9, it'll always be 4 and 6 spaces apart from the two frogs. We could have 1, 3, 7, or we could have 1, 3, 9. So the first case, so expected value of 444 equals to 1/2, or equals to 1/2 of expected value 2, 4, 6, and we need to add 1 because we already made one move to get to this configuration from this one. And then, so that's half of the equation. Now we consider a case where the frog at point 12 moves the other way to 11. Then if 8 moves to 9, we get this configuration again, 9, 11, 3. This is 4, this is 2, and this is 6. But if the frog from point 8 moves to point 7, we remain in a 4, 4, 4 configuration. So each of these two has a probability 1/4 of happening. And we can just combine the first two to get 3/4. To get this equation that will help us determine what E of 444 is equal to. So then let's find an equation relating E of 246 with these two other expected values. So an example of this is 2, 4, 8. We can see 4 and 2 are 2 spots away, 4 and 8 are 4 spots away, and 8 and 2 are opposite each other on the 12 gon. So there will be 6 vertices away from each other. So let's consider what happens. So this time the situation is not symmetric as it was in 444, so we'd have to do several different cases. So let's see what happens if the frog at point 2 moves to point 3, then the probability that it's over would be one half, and the probability that the frog at point 4 goes all the way to 5 is also 1/2. So overall, since there was a 1/2 probability of frog 2 initially moving to frog 3, the probability of this step of the procedure being over will be 1/4. Now we consider what happens when this one here moves to point 3 and the frog at point 4 moves to point 5. Then if the frog at point 8 moves to point 7, we get 2, 2, 8. And if the frog at point 8 moves to 2, 2, 9, we get 2, 9. Then we get 2, 4, 6 configuration, and each of this occurs with probability 1/8. So then we have to consider the case when the frog at 0.2 moves all the way here to 0.1. So if the fog at 0.2 moves all the way to fog 1, then we have still two cases to consider. If fog 4 moves to 0.3 here or to 0.5 here. If the fog 4 moves to 0.3 here, then we had fogs at 1 and 3, and then the fog at 0.8 would either move to 9 or 7, but it's symmetrical. We get the 2, 4, 6 configuration either way, because just look at 1, 3, 9. 3 and 9 are opposite each other in this case, and the other case, 7 and 1 are opposite each other. So the probability of that happening is 1, 4. And then there's one final case to consider. Suppose that the fog at 0.2 had moved to 1 and the fog at 0.4 moved away to 5. If the fog at 0.8 moves to 7, then we get 2, 4, 6 once again. But if the fog at 0.8 moves to 0.9, we get the 4, 4, 4 configuration. Let's simplify this to what do we get? We get 1/4 of this. Three. Plus 1/8 of this. All right, so all right, so let's come back to that later. So now let's consider the 2, 2, 8 configuration. So then a example of this is two fogs at points 2, 4, and 6. So in this case, you have 2 and 4 two vertices apart, 4 and 6 two vertices apart, and then 6 and 2 all the way across, and that's 8 vertices. So let's say that the fog at 0.2 moves to 0.3. Then there's a 1/2 chance that the fog at 0.4 moves over to 0.3 and we'd be done. So the probability of that happening is 1/4. And otherwise, so right now we're only considering the case that the fog at 0.2 moves to 0.3, and then the other case is that the fog at 0.4 moves to 0.5. Then this would be over if the fog at 0.6 moves to 0.5 as well. The probability of this happening is 1/2 times 1/2 times 1/2 is equal to 1/8, and the other 1/8 is puts the fogs at points 3, 5, and 7 after that, which is exactly the same as the original configuration that we had. And so that would be plus 1. All right, so that's the first half done where the fog at 0.2 moved over to 0.3. So now let's consider fog 2 moving over to 0.1. So our first case we consider is fog 4 moving over to 0.3 here. So then there are two choices for the fog at 0.6. If he moved over to 5, we have fogs at points 1, 3, and 5, and that is the original configuration 2, 2, 8. If the fog moved over to 7, we'd have the 2, 4, 6 configuration. Right, and then the other case was that so we already knew that. So we're only considering a case that fog 2 moved over to 0.1 now. The other case for fog 4 is that it moved down to 0.5. So now if frog 6 moves over to 0.7, that is the 2, 4, 6 case once again. But if the frog at 0.6 moves over to 0.5, we'll be finished. So the rest of this would be so simplifying, we get 1/2 plus 1/4 here as well. So that doesn't seem all that hard. So now it's a system of 3 equations. I'm gonna multiply it out first to try to make it a little bit easier to solve. So let E of 4, 4, 4 be equal to A. Let E of 2, 4, 6 be equal to B, and let E of 2, 2, 8 be equal to C. Then we have multiplying the first one by 4, we get 4A is equal to 3B plus A plus 4. So then you cancel, yeah. Just to remind, we're solving for A at this moment. And let's look at E of 2, 4, 6. We multiply both sides by 8, then we get 8B is equal to 2 plus 2 C plus 1 plus 3 B plus 1 plus 8 plus 1. That equals to that would equal to A plus 3B plus 2C plus 8. I'll simplify that, and let's look at this one. Multiply each side by 4, we get 2C equal to 2 plus 1 plus. So yeah, it does not look really that bad at all. So let's see. This one would get B plus C plus 4. So 2C is equal to, or C is equal to B plus 4. Is that right? Oh wait, my bad. It was 4C is equal to B plus C plus 4. So we subtract and get 3C is equal to B plus 4. All right, so then let's just plug everything back in and get A is equal to B plus 4 over 3. C is equal to 1/3 B plus 4 over 3. So then 5B is equal to A plus 2C is equal to 5 over 3 B plus 12. I believe that's right. I'm gonna check, but yeah, I think that's right. 10 over 3 B is equal to 12. Wait, I must have done something wrong, but because that was not what I got before. But either way, you get how we do this problem using expected values. I'll come back. I'll probably come back to this later. But actually, I want to go to this fourth problem here with the geometry diagram first. Okay, so this is from the 2015 Amy 2, and it was number 11. And we have this circle here with points A, B, and C on it, and with center O. the line passing the O perpendicular to OB is line PQ, where P is on AB and Q is on the extension of line BC through C. So we are given AB is equal to 5, BC is equal to 4, BQ is equal to 4.5, and they want us to solve for BP. Okay, so the first thing we do is, well, so we can draw the perpendicular bisector of BC and BA, and those are ON and OM OM and ON respectively because of the definition of the circumcircle. So now we get BM is equal to 2, MC is equal to 2, and QC is equal to 1/2 on that side. And on this side, BN and NA, BN is equal to 2.5 and NA is equal to 2.5. So let's just look at right triangle QOB first. So when you draw the altitude from the to the hypotenuse of a right triangle, you create 3 smaller similar right triangles, or you create 2 smaller right triangles. Alex, I'll get to that right after that. But you create 2 smaller right triangles that are both similar to each other and to the and big triangle. So by similar triangles, so we have triangle QMO is similar to triangle OMB. So QM times MB is equal to MO squared, and MB was given us is 4/2 is equal to 2, and MQ is 2 plus this 1/2 section, which is 2.5. So MB times MQ is equal to 2 times 2.5 is equal to 5, and that means MO here is √5. And then you use the Pythagorean theorem on this triangle with MB is 2 and MO being √5 to get BO is equal to 3. Okay, so now we will find ON. We know that BN is half of BA, which is 5/2. So using the Pythagorean theorem on triangle BON with BO equals 3 and BN equals 5/2, we get ON here is equal to √11/2, 5 square root of 11 and 6, because 3 is basically 6/2. So ON is equal to, I'm going to draw. So ON equals √11/2. So this is so basically this is 2, 1/2 √5, 3, 5/2, and 11/2. All right, so then we can just use similar reasoning as we did on triangle QOB on triangle BOP. So that means ON squared is equal to BN times MP. ON squared is equal to 11/4. So BN is 5/2, so 5/2 times MP is 11/4. So that means MP is equal to 11/10, just by direct division. So then how do you find BP? You just sum BN and MP. 5/2 plus 11/10 is equal to 18/5, and therefore the answer to this question is 23. Uh-oh. All right. Do we have any time for this third one? But I'll start, and I'll start this question anyway. It seems to be really. It seems to like a pretty. Yeah, that's a pretty cool, very clear drawing. Okay, that's a pretty nice problem actually. All right. So this is 2016 Amy 2 number 13, and this actually seems to be pretty difficult. So Beatrix is going to place 6 rooks on the chessboard, and in chess, rooks attack each other if 2 are in the same row or in the same column. So she wants to place 6 rooks so that no 2 are on the same row, same column. So 1 in each row and 1 in each column. So the value of a square is the sum of its row number and column. And in this case, I'm just going to assume value from left to right. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we know that we are looking for the average score over all value configurations of 6 rooks, and the score is the least value of any occupied square. So since there must be a rook in this square, so we know the maximum possible value of the score cannot be greater than 1 plus 6, which is equal to 7. So let's start with so first of all, the total number of possible configurations is 720, because this first row there are 6 choices to place a rook, and the second row there's 5 choices because you can't put it in the same column as the first row, and then there's 4, 3, 2, and 1 choice for the rest of the row. So the total number would be 6 factorial. So then so the minimum possible score is obviously 2, which is 1 plus 1. So we'll do it using this way. All right, so every single configuration has a minimum score of at least 2, right? So there are 720 configuration for a minimum of at least 2. So now let's go to this. Well, yes, you're right, and I'll just show how that works. So then, well, I'll do an easier way for 3. So the number of configurations in which the score is at least 3 is just equal to 720 minus the amount that has a score of 2. And the only way you could have a score of 2 is you have a rook right there, and the probability of that happening is 1/6. So then it would be 720 times 5, 6 is equal to 600. Now, as we go to 4, 5, 6, or 7, it does start getting a lot harder. So let's just say, so we want to find the minimum, the number of configurations in which the score is at least 4. So that means no rooks can be placed in these 3 spaces, and then without loss of generality, let's just put rooks right here and right here. So then you can't put rooks in this area now. Now, what do you get after this? You basically get a 4x4 square where there's no restrictions now. So the number of ways to fill the rest of the grid is 4 factorial is equal to 24. There's 4 choices to choose here and 4 choices to choose here, and they're independent of each other. So the number of configurations with minimums with score at least 4 is equal to 24 times 4 squared, and that is equal to 384. All right, so let's see. So all right. So now let's go to the case where the score is at least 5, which means these 3, which means 3 more blocks cannot have squares in it, or cannot have rooks in it. Oh, well, because like so Alex asked the question, why did I put rooks on 3, 1, 1, 3 and scores greater than or equal to 4 case? But so let's just look at that again. So we know there must be a rook in row 1, and we know there must be a rook in column 1. And they're independent of each other because you can't put a rook here at 1, 1. That's the intersection point. So wherever we So wherever you put rook on this row, it blocks this first row and 1 full column, and same here. All right, so now let's go to the case with where the score is at least 4. All right, so at least 5 now. Actually, we just did 4. So then let's start. So let's start with putting just use the method again. Put rooks at 1, 4, 4, 1. So basically here you can't put rooks anymore. So now this is still a little tricky. It's still not a whole square yet, although it's pretty darn close to 1. It's just a 4x4 or a 4x4 square minus 1 point. So it's basically just the 4x4 square except you take away a vertex, which is pretty similar to the case we did earlier, although they're not the same. But without loss of generality, let's put 2 more rooks right here, and here. And then there's only 2 ways to place the remaining of the rooks. So let's go back and see how many ways there were to do this successfully. Oops. All right. So the first 2 rooks, there were 3 choices to place over here and 3 choices to place over there. So that means there are 9 choices there. And then for the 2 rooks here, there were 3 choices in this row and 3 choices in that row because you couldn't place rooks in this or here. So there were 9 choices to pick the first 2, and there's 9 choices to pick the second 2, and then there's 2 choices to pick the final 2. So that means the number of configurations will score at least 5. For the 9 times 9 times 2 is 162. Now let's go to scores greater than or equal to 6. That means even more points are blocked off. Why don't I just place the rooks column by column instead? Well, I could, right? But I'll just like, let's say like, but sort of like I want to do row and then column because they're symmetric, because there's only 2 places. There's symmetric across this axis on this side. Like if I wanted to do column by column, there's 6 choices to place here, 6 to place here, but only 5, 4, 3, 2, and it ends up being dependent on each other. The number of cases where a rook is over here is different from the number of cases in which a rook is here or here, say, because then there's like more restrictions basically. What if I do it left to right? Placing the rooks column by column is basically equivalent to placing the looks row by row because this figure that we have is symmetric across this negative across this negative axis shown right here. So the best way to do it is just to do it symmetrically and consider row and column. Right, let me erase that first. All right. So now let's do head to the case where the score is at least 6. So these are the points we cannot put any rooks on. So let's assume, so now there are very few choices to put rooks in this row 1 and column 1. So let's just state these 2 points here. Oh, that's so bad way. All right. So then we get something similar to a square, not quite, but it's basically like this. All right, so then we need to find a number of ways to put 4 rooks here to satisfy the restrictions. So let's say we put one over here and one over here. That's again, so there were 4 ways to place the first 2 rooks as being 2 times 2, same in this case, and the rooks that will be erased, I'll erase them now. So this one's gone, this one's gone, these 3 are also gone, and on this side, you got this one gone, this one gone, this one gone, and this one gone. And so what remains is a 2 by 2 square. And obviously there are only 2 choices to place the rest of the rooks. So in the end, the number of configurations with score at least 6 is only 4 times 4 times 2 is equal to 32. And that makes sense in this situation. There's not many ways to place 6 rooks with that many restrictions. And obviously, if the score is greater than or equal to 7, then there's only one choice. Place them all in this diagonal here. All right, so, okay. Okay, so let me read that. Okay, I meant in the first column there are 2 choices, and the second column has 3, you're right, and the one is attack, so there are 2 choices. Well, yes, you could do it that way for sure, and it does, and I think it does work. So, all right, so let's just do this 6th configuration this way. All right, let's start with the first column. So you can definitely do this. Let's say here. Then, all right. Then there are 2 choices here. There were 2 here. And let's do that. So it does end up looking very nice. And then there's 2 choices here. 2, and then 1. So that still ends up being 32. And then I'll try one with this one as well to see if it actually works in that situation as well. But it seems like it does. It is a way to do it for sure. All right, so let's erase these. All right, let's go again. All right, let's try here. 3. There's also 3 choices here. 3. And then there's 2 times 2 but just 2, I'm sorry. So yeah, that's definitely a way to do it. Yeah, right, but row column approach was the first one I saw that I thought was the best to use. But you can definitely do it this way for sure, and it does give you the right answers. All right, so let's go back and find the total number. So if the number of configurations of minimum score at least 2 is 720, and the number of configurations of score at least 3 is equal to 600, then that tells you the number of configurations score equals 2 is equal to 120. And then we just do the same for the rest. So I'm just going to check if they add up correctly. 123, 36, 558, 6, yeah, so they add up to 720 as expected. All right, so let's see. 2 times 120 plus 3 times 260 plus 4 times 222 plus 5 times 130 plus 6 times 31 plus 7 equal to 240 plus 648 plus 888 plus 650 plus 186 plus 7. And that equals, well, this is actually not very easy to add. I'm going to tell you that. 876, 248, 88, 17, 76, 24, 26, 20. I believe it adds up to 2,619. And when you divide this by 720, I think it gives you 280 291 over 80, and the answer, so therefore P is 291, Q is 80, the answer is 371. So this problem, it sort of looks intimidating at the beginning, but once you figure out the way to calculate, given that some squares are not allowed to have roots, then it is manageable. All right, and I think that's all I have for today. So thanks for listening.